Well, one of the things we learned in calculus was that circle was not a function, right? And a sphere was not a function. And so in order to accommodate that and still work with circles and spheres analytically, what did you have to do? You have to transform the equation or equations from Euclidean space to spherical coordinates. Remember that? Because in spherical coordinates you could represent a circle or a sphere as a function. Whereas in Euclidean plane you can't do that. So sometimes it's convenient to do that transformation from the Euclidean space to spherical coordinates. Also, something else that you've done is that you have two variables that you were plotting in the Euclidean plane, and then you changed. And so, for example, the plot that you got might have looked like a curve that's climbing exponentially. And so you switched it, transformed it to log. You replotted it on log paper, and you got a straight line instead. And sometimes it's handy to do that, because in the log-log plane, what was a curved line now becomes a straight line, and it's much easier to work with. So sometimes, in econometrics, and we're going to see why later, it's convenient for us to make certain kinds of transformations. And what you just showed me was something that I was just doing off the cuff. What I suggested was that sometimes we might be looking at an ellipse. And the ellipse that we're looking at is an ellipse. An ellipse has two axes. There's a long axis and a short one. And sometimes it's the case that ellipse is the long axis of the ellipse is at some angle to the horizontal axis or some angle to the vertical axis. So it's a little bit askew in the plane. And for analytical reasons, it's sometimes easier to tip the ellipse back so that it's horizontal and tip it the other way so that it's vertical rather than be skewed to the axis. And sometimes it's of interest to squash the ellipse so that the two axes of the ellipse are the same length. The question that you brought up was how you do that. Well, an ellipse, the representation of an ellipse in the Euclidean plane is a quadratic form, right? And so that discussion came up as to how do we change that quadratic form, which has cross products in it. Suppose that the two axes are called x1 and x2. So the equation for an ellipse is ax1 squared plus b times x1 x2 plus c times x2 squared. Is there a way to rewrite that quadratic form so that it involves only squared terms that gets rid of the cross product, and so in effect what we're doing is tipping the ellipse onto one axis? And then is there something else that we could do to get the revised coefficients on the squared terms, rescale them somehow so that they're the same? Because if they're the same, then we have a circle. And so the question that I posed was, how do you do that? Well, if the quadratic form you start with is positive definite, means it's a full rank, then it has, and suppose the rank is n, corresponding to the number of rows and columns. So if it's a full rank, then it means that there are n unique characteristic groups, and there's a characteristic vector that corresponds to each one of the characteristic groups. And we know from linear algebra that once we find the characteristic vectors, and we assemble them into a matrix that we call C, the matrix that we started with, A, is equal to C transpose, right? That's one of the things we look about characteristic vectors. So suppose that you've done that work. We have found the characteristic vectors, and we've put them in C. And so we know that A is equal to C transpose. So we multiply through by, so we have found the characteristic vectors. When we multiply CA, C transpose, what do we get? What's the result that we're going to find? If we multiply a matrix by its characteristic vectors, and then multiply by its transpose, what do you get? You get a matrix that has the characteristic groups on the main diagonal. So we'll call that lambda. suppose that we come up with another matrix that we'll call D, which has on, that's diagonal, but it has on its main diagonal 1 over the square root of characteristic groups, the eigenvalues. Now, suppose that we constructed D times C A, C transpose D. What's that going to do? What do we get? We get an identity matrix, right? So now, just for the sake of argument, suppose that we had the quadratic form, x transpose AX is equal to some number. Okay? So not only is it an ellipse, but it got shifted away from the origin by some amount, a little bit. And so A is filled everywhere. There might be some zeros in the exact numbers almost everywhere. Not just a diagonal. Scalar, it's not a scalar diagonal matrix, so it's not a circle. That's one diagonal. It's an ellipse. And we've got enough numbers in the off diagonals so that the ellipse has been tilted. Suppose that we constructed, suppose we did that. Is there any difference between the first line and the second line? No, because C inverse C is, C inverse C is the identity matrix. It's just like multiplying by 1. D inverse D is the identity matrix. And the same thing happened over here. So let's play a little game. Let's call this part. Let's call that Z. Z. We'll call that delta. And we'll call this part D. And I'll call that D transpose. And we'll call this W. So if A is n by n, then in n-dimensional space, that's an ellipsoid tilted off from any of the axes. But in the space spanned by the W's, or the W space, it's a circle. So that was the only point that I showed. And the reason that becomes of some value to us, you may recall from your beginning statistics class where you had first were exposed to regression analysis that you had a garden variety simple regression which said that yi is equal to alpha plus beta times xi plus ui, and you had a bunch of observations and said that the ui are distributed identically and independently as a normal with some mean mu and variance sigma squared constant plus all the i's. In that case, a joint distribution of the error term u is a multivariate normal. So if little n was 2, imagine it's a mountain that's perfectly symmetric no matter how you look at it. That would be a bivariate normal. And if little n is something other than 2, then in that multidimensional space you've got a mountain that is perfectly symmetric in any dimension. So when you look down on the mountain, how many people have have studied economics in the past? A whole bunch of people, many. How many of you remember talking about indifference curves? Some of you. An indifference curve is the combinations of two goods for which the consumer gets equal satisfaction. Or in production theory, you talk about isoquants. It's the combinations of, say, capital and labor that yield the same amount of output. And even though you know that those indifference curves come out of a three-dimensional picture, we draw it in 2 dimensions, and the indifference curves tell us something about the shape of the three-dimensional picture, because the indifference curves are the same height off the horizontal plane in the utility commodity space.